It's my pleasure to introduce Rolf Sager, who is a project scientist here at the Beckman Laser Institute. He works in the diffuse optics and the spatial frequency domain imaging laboratory and has worked on a lot of different problems, but he's very passionate about optics, taking accurate measurements, developing good computational models to interpret these measurements. And this year we're doing something new in the workshop is that you'll see this afternoon, you'll actually get the opportunity to make some real measurements and understand what is necessary to take data and pre-process that data such that it is usable or interactable with these modeling and computational tools. So, and as I alluded to earlier, we're going to continue to pursue this idea and this understanding of how you deal with extracting optical properties from finite tissue slabs. And so Rolf will give us an introduction to the techniques, historically the techniques used to do that, and they will couple very nicely to your afternoon lab activities. So, Rolf?
Thanks, Boston. So, yeah, this presentation today, this lecture is actually going to be quite different from the other lectures in this workshop because since the lab itself is going to be designed to give you more of an experience of the kind of physical limitations and the experimental considerations you need to do when trying to use inverse solvers, I'm going to try to keep this somewhat light and again talk about this one particular model, this inverse adding doubling method, as it is the kind of first inverse solver used in biomedical photonics. So the teaching objectives here are just to give you some idea of how adding doubling is an exact solution to the radiative transport equation. And again, Boston, earlier today and throughout the rest of the lectures, there's going to be a lot of discussion about approximate solutions and different methods that you can exploit analytical models for distinct regions of optical properties. This one is actually exact and how it can be used to describe slabs of tissue. And of course, there's going to be certain embedded assumptions involved with this. Then how we can use these solutions which will model the total reflectance and transmittance to actually infer the embedded optical properties used in the forward model. So again, this is the inverse solution. And what does it actually take to actually measure reflectance and transmittance and employ this inverse adding doubling method in an experimental setting? So the general outline for this talk, just again, from the first day of lectures, there was an introduction to forward and inverse models. I'm going to just reiterate that right now, and then go into a little bit more detail about the forward model of adding doubling. Again, for this talk, I'm going to try to avoid as many equations as possible, so this will be more of a general description and not any detailed derivation. Then go into the inverse model. Again, how the solution would work for idealized measurements, what considerations you need to make for physical measurements in terms of instrumentation, calibration, and preparation of samples that you would actually measure, and strategies for managing these experimental conditions. Then try to summarize it with some just general rules of thumbs and take-home messages, and time permitting, some examples of inverse adding doubling actually in use. And then try to put inverse adding doubling in the context of other inverse solver methods and other techniques that will be described with the final 2 days of this workshop. So again, to kind of give a little bit of a refresher from the first day, forward model in general terms describes what happens to light in media as a function of the properties of that media. And so again, absorption, scattering, anisotropy, the index at boundaries, so on and so forth, and that these models will generate outputs, which are typically in terms of radiance, either within the volumes or at the boundaries. So again, I'm using radiance a little loosely here. And that with the inverse model, The idea is to infer those optical properties of tissues based on the measurable outputs of the unknown medium. So again, as Jerry had introduced very early on, that when it comes in terms of measurable outputs, often they are not sufficient to fully describe all the input properties used to generate these outputs. So again, this is this kind of ill-conditioned or ill-posed type of a problem. However, if you have a careful selection of a forward model, assumptions on the tissue properties and distributions, apply constraints to the measurement geometries, and also employ different experimental conditions, perturbations of sources, detectors, so on and so forth, inverse solutions are achievable under very specific circumstances. So this will be repeated several times in this talk, but just want to remind you that there are a variety of models and methods that have been developed to date, and these different forward models to describe light transport all have their strengths and weaknesses. And in terms of placing these in practice, there's always different types of trade-offs that you will have for these. And again, computational processing speed versus accuracy, whether you need to have results fast versus accurate, measurement complexity, what different things you have to actually have to actually acquire complementary pieces of information versus acquisition time, sensitivity to spatial heterogeneity and other structured aspects of skin as opposed to just assuming homogeneous distribution, and also the practical method of instrumentation costs. And so the key to successful research is to understand when and where, it should be and, each method it is best to address the problem that you want to address. So understanding what your options are, what the problem is, and which ones will work best is the basic idea here. So that's just kind of a little refresher on general concepts of forward models using inverse solvers and which directions they go. So to kind of give a general description of the adding doubling method, so what it does is it calculates the reflection, or I'll be referring to it as reflectance and transmittance of light through a single thin homogeneous layer. So this is just a very basic concept. You shine light. It's a method of interpreting what goes on within the volume. So it generates an operator that will describe it, and it just outputs what happens on either side of the slab to the light that's put in. So when we refer to doubling, why it's called adding doubling, doubling is the property of this particular model where if you have an arbitrarily thick sample, you can actually use a thin slice and propagate that for any arbitrary thickness. So you can actually perform a calculation, a forward model for a thin sample with absorption, scattering, anisotropy, and then double it, essentially, to any thickness, arbitrary thickness that you want. So likewise, in terms of adding, it's an extension of this property where now, since you have descriptors of individual thin slabs, you don't necessarily need to have the same optical property for every single slab, but you can then propagate the light through different optical properties in different slabs. And so this, in particular, in terms of the inverse solver, we won't be able to necessarily discriminate in depth by using this method, but in order of describing a practical aspect is that if you're going to be measuring, say, tissue, typically it's going to be sandwiched between two glass slides. And so this is a typical configuration where if you know what the optical properties of the glass slides are, namely the index of that, you can then go through and actually propagate light through a sandwiched pieces of glass and actually make those calculations. So there's ways of accounting for these different layered structures. So that's in general, but going back to how does it actually propagate light through a thin slab? So from the second lecture, Jerry had gone through and had this simplified description where essentially adding doubling, the first thing it does is it takes radiance, which is 6-dimensional, and simplifies it down to a 1-dimensional representation. And so it does this by assuming that there's no spatial distribution of optical properties, that it's essentially just a homogeneous slab with infinite extent. That gets rid of your x and y dimension, or in this case, y and z dimensions, so you have a single spatial dimension. And then it also sums over all the angles in radiance to have a single property. And by doing this, it simplifies the radiative transport equation tremendously, that you can apply just a very simple solution to that problem to describe the forward and backward directed radiance derived here. And again, the stress here is the fact that this is an exact solution under the condition that we are collapsing this 6-dimensional space into 1 dimension. So to actually describe how this process actually works, if we look at a slab and we have our radiance, and so again there should be a minus sign over here and minus sign over here indicating the direction. So it's either forward or backward directed radiance, that you can go through and describe how light would propagate, and in this case, light exiting the slab here. You have your input radiance, and this t going from boundary 0 to boundary 1 is this internal operator that would describe how the optical properties would affect the incoming radiance. And this operator here, r, from boundary 1 to 0, would affect the backward directed light. Similarly, to find out the light that would exit at the top of the surface, so this would be your reflectance, would be managed by the operator going from the 0 boundary to boundary 1 with the incoming light, and the transmittance operator from the negative direction. So this basically, in the end, for a single slab, this L1 in the positive direction would be your total transmittance, and your radiance in the negative direction at the top of the surface would be your total reflectance. And so what happens now is that in terms of this doubling aspect, is that if you add another layer here, then this positive going radiance would be entering that slab, which is described here, would then be submitted as this L1 or L0 into that slab, and you can basically substitute this value into this for the next operator. And so you can kind of continue to propagate these with these different operators. And these T and R operators are defined, again, driven by these solutions of the one-dimensional case of the radius transport. So I'm not going to go too much. This gets into a lot of linear algebra because basically this method was set up in terms of matrix operators, but there are several references here that will describe that in more detail. And you can note that this goes back to 1962. So this has been around for a while. Originally it was developed to describe scattering in the atmosphere. So that's what this paper was all about. But since then, it's been also applied for any kind of turbid media that is in forms of slabs. So hence, starting out in biomedical optics to actually understand optical properties of ex vivo tissue, this was the simplest way to start to explore exactly what's going on. So, how is this a powerful tool? Well, like I said, it's an exact solution of the RTE. So there really is no restriction to the ratio of absorption or scattering to absorption So it will work across practically all optical wavelengths. The caveat there is this does not account for fluorescence. So this is all wavelengths where the optical properties are just described by the absorption and scattering. So radiance is only described by absorption, scattering, and anisotropy. There's no restrictions in your range of scattering anisotropy for this problem. And this also will account for internal reflections at boundaries. And again, there's always this issue of boundaries and index mismatching between air and tissue, or air, glass, tissue, so on and so forth. And this model has been developed to actually account for that, typically in terms of Fresnel reflections. So, yes, yeah.
So Rolf, I just wanted to know if you could comment on how the phase function is handled. So you say that you can do absorption scattering and single scattering anisotropy. Is there any underlying assumption for the form of the phase function?
So typically, the underlying phase function is described through Haney-Greenstein. But in the case of collapsing everything down into one dimension, you're just integrating over all the different angles. So, that's where the kind of simplification comes through. But yeah, there is that distinction. So, even though this is a powerful tool, it also has several key assumptions to make this model so simple. And so, again, this is based on a steady state solution, so there is no time dependence to your source. The layers must be uniform, so finite in thickness, and infinite in lateral extent for this idealized solution. The absorption and scattering must be evenly distributed within the volumes of these layers. And the illumination is uniform, though it can be collimated or diffuse light. There are two separate classes of solutions based on that. So, but in summary, again, adding doubling is a forward model that describes the total reflectance and total transmittance at the boundaries of the layers. So again, this is not optimized to describe fluence within volumes. This is literally just a transport operator between boundaries in physical thicknesses. This model simplifies radiance into a one-dimensional function by assuming lateral heterogeneity, so you have one spatial dimension, and integrating over all scattering angles. So this then goes through and simplifies the model and reduces the number of input parameters. And again, this is always this condition of ill-posedness. It now simplifies to only 5 different parameters, where you have absorption, you have scattering, you have anisotropy, the index at the boundaries, and the physical thickness. So by assuming values for the index and anisotropy, and actually measuring what the physical thickness would be, it's then possible to really just describe reflectance and transmittance in terms of just 2 parameters, namely absorption and scattering. So now you have two measurements, 2 unknowns. That's something that will kind of meet that kind of ill-posedness condition in an idealized case. There's always that caveat. So just any general questions in regards to the forward model of adding doubling? All right, wonderful. So from the forward model then, how do we get to the inverse solution? So again, as I just mentioned, you now have this 5 parameters of inputs for your forward model. And again, to make life easier, you can always translate them into dimensionless parameters. So again, our friend albedo, and this tau is referred to as the optical thickness. So now you basically have 2 inputs with an assumed G and assumed N. And you have measurements that you can generate from an exact solution that would now describe your reflectance and transmittance in terms of your positive and negative radiance on the boundaries of your slab. So, and again, knowing the index of refraction, you can manage surface reflections at the boundaries. And again, your G can be, is typically assumed to be Haney-Greenstein to describe the G. And now for our inverse model is to find absorption and scattering as a function of reflectance and transmittance, where the forward model would describe reflectance and transmittance in terms of absorption and scattering. So inverse adding doubling as a technique involves an iterative strategy, and this is basically the steps that it takes. So first, guess a set of optical properties. Calculate what the reflectance and transmittance would be from your forward model for those specific optical properties. Compare the calculated values to the measured values you have. Test for goodness of fit, and repeat until you can find a match or at least minimize that problem. So that's, in general, for many inverse solvers, the method and approach that you do. So you run your forward model, see how close it is in agreement with your actual measurement, update your guess in some intelligent way, and I believe tomorrow Carol will be talking about methods for minimizing those differences, amongst a lot of other things. So, but that's the basic concept. So, okay, so now you can run that. You have an approach that you can actually try to go through and minimize your reflectance or your optical properties in terms of reflectance and transmittance values. But it's also important to know in terms of the range of reflectance and transmittance values and the pairs that you would actually measure out of a physical system to really understand, even though it's an exact solution, how sensitive would you be in terms of reflectance and transmittance to accurately determine the optical properties present. So again, this is beginning to try to fold in the actual physical measurement of doing this. And so this is just, again, a plot taken from one of Scott Prahl's paper, looking at the albedo and anisotropy over a range of total transmittance and reflectance values. And so what you can see is that this mesh for a specific tissue condition, but variable optical properties, that it's not very linear in terms of where the parameters would lie versus what the optical properties are. So namely, once you start to get to very low reflectance and low transmittance, this kind of parameter space of optical properties begins to collapse, indicating that there would be ranges where you have to be very accurate in order to measure in terms of reflectance and transmittance in order to produce reasonable or accurate optical properties. So one way of doing this is also just reparameterizing the problem. And what you can find is now you have this new parameter space where if you overlay this solution mesh over the actual reflectance and transmittance, you get a bit of a wider range of solutions, and particularly over the range of reflectance and transmittance values, you get pretty well distributed solutions. And also, when you consider the typical range of tissue values in terms of the optical properties, that you have now a space where when you expect certain amounts of, of absorption and scattering that are typical for tissues and the thicknesses of tissues that you would measure, you now have something where you can see that it's going to have a pretty forgiving range of reflectance and transmittance values in order to actually get to accurate optical properties. So, any questions in regards to the idealized inverse adding doubling solution, the inverse solver?
You said that, like, you basically guess, choose values, calculate R and T based on that, and then repeat until essentially your system is optimized. is that like written in the model, or is that basically like a guess and check and you change them how you think?
Yeah, I mean, there's ways of intelligently updating your guesses, but the idea is that you want to have your measurement and your forward model solution be the tightest match. So the idea is that, every pair of reflectance and transmittance values maps directly to a unique solution for absorption and scattering. So whatever your measurement is, again, with assuming G, assuming index, and knowing what that thickness is, that you can go through and just find a path of guessing, updating, and minimizing that solution to the unique value in that parameter space.
Thank you.
That's automated, right, just to clarify.
Yeah. Yeah, it's, yeah.
That
Yeah.
process is automated.
Yeah, and that's what Carol will be talking about, is how do you actually automate that process. So, and there's multiple strategies of doing that, so don't want to give away all the fun though. So now from this idealized sense of this inverse model, how do we actually now translate this to a physical measurement? So again, the main question is how do we actually measure the total reflectance and total transmittance in a physical sample? So from our model, it's one-dimensional. It's based on integrating over all angular contributions in a single dimension. So the general question is well, how would we actually go about detecting light over all angles on either side of the slab? So you can't really just put a detector in front of it. There's going to be some numerical aperture of light collected, or only a small subtended angle of light that you can collect. This is now assuming everything from 2 pi over the solid angle. How do we detect and integrate all those photons? So the answer is using an integrating sphere. So the general setup of instrumentation to make measurements of this type involves a source, typically collimated, and the source can be a laser, it can be a single wavelength, or it can be broadband, and paired with that you could either have a single APD or some detector to detect that single wavelength of light, or a spectrometer to detect all the wavelengths from your broadband source. But it's collimated and then enters this integrating sphere, and the integrating sphere basically says that if you shine a narrow beam of light or a collimated beam of light through your sample from the transmitted side, that even though light will be scattered when it interacts with that slab, that putting it in close proximity of the entrance of this, that it will collect all the lights scattered at all angles from that sample, allow it to bounce around within that sphere, and that you sample a small portion of that, which is now all evenly mixed. So again, all angles of light, and is sent to a spectrometer and detected that way. Likewise, for the reflectance, if you put it on the opposite side of the sphere, your collimated beam goes straight in, hits the sample, and again, the diffusely scattered light will bounce around, integrate within the sphere, and be detected by the sample. So that basically just follows up with what I was saying with this slide. So again, the idea here is with the reflectance in terms of the Fresnel reflectance at the surface, the index mismatch boundary conditions. It's the fact that at the surface of your sample here, you're going to get light reflected out of the system. You need a way of accounting for that. And likewise, light that is specularly reflected from your reflectance will exit out of that same entrance port that you brought the beam in. So when you're integrating these signals, it's just from the scattered light, not the light that was reflected off the surface and had not interacted with the sample itself. So that's the basic configuration of an instrument. That's how you would try to measure the total reflectance and transmittance. But it's also good to remember that this is a physical experiment. So integrating spheres are not perfect. So certain things you have to remember about it is that the reflectivity of the wall is not 100%. Typically, it's around 99, 98, depending on how much money you're willing to spend on these things. Not all angles are integrated. So again, you have this large sphere, and you have holes in it. You have holes for your entrance port. You have holes for your reflectance port. You have holes for the detector. So you need to have a way of accounting for the fact that you're close to integrating over all angles, but not necessarily every single angle will be accounted for. And thankfully, though, somebody has really spent all the time and effort to actually figure out and calculate how these imperfections of the sphere will actually address it. And so, this is very difficult to see because I don't want you to even bother reading this, but this has gone through to say, with multiply reflected light within the integrating sphere, how do these imperfections contribute to the total integration of your light signal? So the other thing that you have to consider is calibration. Now, again, you're making a physical measurement. When you make a physical measurement, you have a source, you have it interact with some system, and then you have a sensor that detects a number. So you have to keep in mind that reflectance and transmittance is a relative quantity. It's the amount relative to the amount of light source you have incident on your sample. Likewise, there's also other experimental conditions to consider. Is the fact that detectors typically will have a dark current. In spectrometers, there's always some underlying detected signal even when there's no light present. It's also temperature sensitive. There's a lot of different things that will go on. So you have to know exactly what that is. You could also have stray light going into your system, and that would also provide a contribution to your signal in addition to what you're actually interested in. So typically there's a procedure where you would first make a measurement with your sphere with no sample present. So again, this would give a sense of what 100% illumination would be detected as. So this is kind of your sphere calibration standard type of measurement. And that essentially would be kind of like the upper bounds. You can't get any more light than this. And then you would have your dark measurements, which again would be the lower bound. And this is, again, where typically you should not see any signal. And so this would account for your dark current from your detector, any stray light. And the way you would do this is you would block your light source, but leave your entire system intact. And you would actually, best practices would be to do this for every single type of measurement. So when you make your calibration measurement, when you make your transmittance measurement and your reflectance measurement, you would then just block the light source. That will give your 0 counts. So you would subtract your dark from your reflectance and transmittance, and then you would take the ratio from your 100%, and that would then calibrate your reflectance and transmittance measurements. So once you have those, you can go through and then submit them to inverse adding doubling. So again, lucky for you, somebody has spent considerable time and effort developing a processing code that's freely available on the web, namely Scott Prowl. So the key thing to keep in mind is that running inverse adding doubling is simple when you have perfect measurements. But there's also a lot of imperfections in your measurement system that you need to account for. And he's done a lot of that for you. So with this code, all you need to do is know how to collect and calibrate your data. He has methods where you can input what the specific properties of your sphere, the sphere size, the port diameters, the reflectivity of your sphere, and he has code that will correct and compensate for that. He also has code generated that will deal with the sample geometry. So again, If is it a bare sample, then you have your boundary mismatches between your sample and air. Is it sandwiched between glass? Well, then you would have to go through and account for what is the index of refraction of glass? What is that difference between the sample, and so on and so forth. And so he's already incorporated that into the code and taken care of that for you. And the last thing, and this is probably the most computationally heavy aspect of the actual code itself, is, again, you have to remember that this is not an idealized system. You don't have a sample of infinite lateral extent. Your integrating sphere entrance is not wide enough to measure every single angle or every single photon that goes through your system. Your beam itself is not a pencil beam. It's going to be a beam of physical diameter. Your sample is going to have thicknesses. So there are conditions where there will be light that interacts with your sample that will never reach the interior of the sphere itself. And so what Scott has set up is based on the relative port sizes, beam diameter, and thickness of your sample, and actually technically the optical thickness. It will actually go through and do an additional inverse solving using a Monte Carlo code to actually say, all right, if it was an idealized measurement, this is what the optical properties would be. However, if these are the optical properties, there would be this many photons that would never be measured based on this geometry. Let's correct for it and correct and account for losses of light that never enters the sphere. So that's, again, another huge consideration in terms of experimental measurements. So again, in terms of your sample, other considerations that inverse editing doubling does not account for, surface roughness. Again, it treats everything as a very simple one-dimensional geometry. So that it assumes that you have flat, parallel surfaces of your sample. And again, this is used, and that way you can actually employ Fresnel reflections and Fresnel coefficients to account for reflected light at boundaries. If it's rough, you can't do that anymore. Tissue heterogeneity. So again, if you're dealing with actual tissue, we know that it's all structured. There's a question of uniformity. This code assumes it's homogeneous. So when you're making measurements, you have to kind of consider how heterogeneous is the sample? Can I measure regions where it's more homogeneous than others? How close and how large of a sample do I really need for it to approximate an infinite in lateral extent slab? And thickness variance. So again, as editing doubling suggests, optical properties should scale with thickness. So if you have something that has variance in the actual thickness, when it calculates the optical property, those errors will propagate. So, any questions at this point?
Hi, thanks. If you could go back to the slide where you had a diagram of the experimental setup for the reflection and transmission measurements.
Mm-hmm. This one or
The one
previous one?
Yeah.
Yeah.
So in the part B, when you're doing the reflectance measurement, what sits behind the tissue sample? Is it just open air?
It's open air.
Blacked out?
Yeah. So the idea is that you don't want to have anything behind this because you have, every single time you're illuminating the sample, you have transmittance and reflectance, and you only want to measure the one. So if you have the transmittance, you want to have that just kind of go off into space and not bounce off of something and interact with the tissue a second time.
Okay, so if we put a black mat
Yeah.
behind the tissue sample, it's good.
It's good, if it's really black.
Or free space, let
Yeah.
it just fall off into free space.
Yeah. So, there are different ways of trying to deal with that, but that is always a tricky thing because, you want to just account for those that interact with the sample and enter the sphere. You don't want to have any other sources of light interact with the sphere at that point.
So just want to make sure that on the both diagram, the optical fiber is fixed. You never move that, right?
Yep.
So what you have is when you shine the light to the tissue, let's say transmission or reflection, what you have is just, if you have an optical fiber and a spectrometer, just you're gonna have a spectrum across different wavelengths, and
Right.
you divide it by the reference, and you have something related to the transmission, reflection of
Yeah.
all the angle.
Yeah, so it's the kind of total reflectance or transmittance at every single wavelength. And, this afternoon lab, that's basically the kind of data set you'll be playing with, are just these reflectance and transmittance spectra, and then going wavelength by wavelength to calculate what the optical properties are in terms of that. So the one main difficulty is when you're trying to do something broadband is with broadband light, how do you collimate it? It's not trivial, especially if you want to look at large spectral ranges. So, and actually one of the setups in the afternoon, it actually uses a parabolic mirror, which will address the chromatic issue, but it's a big pain to align. The other one actually has lenses, and so there's going to be some limitations as to what range of wavelengths you can actually collimate, but the idea is just to kind of get some sense of how to do these things. So, single wavelength laser sources, they're really easily collimated. You don't really have to worry that much, but then you only get reflectance and transmittance at a single wavelength. So there's always these kind of trade-offs with these types of systems. So.
I have a question. When you couple light into the fiber, so you basically lost lots of mode. I mean, if you use like multi-mode fiber or like single mode fiber, does the model can account for that loss or?
So those losses are usually accounted for in terms of the calibration. So with your detection fiber, you're only sampling a small part of the light that's been integrated within the sphere. So, this tends to be, again, in the later slides, I'll actually go into a little bit more detail that this is a very lossy type of measurement. So signal and noise is always a big issue. Actually having accurate detectors and a sensitive enough spectrometer comes into play. But yeah, there's lots of loss in the system in order to actually have a nice clean collimated beam and control the beam diameter. You end up rejecting a lot of your source illumination because you have to put an aperture in and control that. And then with the detector, you can have a multi-mode fiber, anything that will actually fill the slit as most efficiently as possible with your spectrometer are ways to manage. But you're only looking at a small fraction of the total light interacting with the system. All right. So, it's getting a little slow. So, to kind of wrap this up, just wanted to have kind of again, some rules of thumb to kind of consider when actually considering using this type of method. And again, as mentioned several times already, you just need to understand the practical constraints and limitations of the model to best exploit the advantages of the approach. So with inverse adding doubling, the first rule is minimize measurement non-idealities. So the merits of this transport rigorous solution by collapsing it down in one dimension also makes the actual geometric considerations that much more important. So by simpling the geometry, it makes the measurement much more difficult to do. So, questions of sample thickness, thinner samples would help minimize the practical aspect of side light losses. When you look at the optical thickness, there's a certain range with that one figure that I had shown up very early on that would be ideal, that you would want to do in order to kind of make the parameter space of your minimization and detection of optical properties as best as possible. And also, the thicker the sample, the more absorption events that will happen, the less light you would actually get through. So there's complications in signal and noise. And also with the scattering, you're going to have more light losses that way. And then also with optical thickness, since this is a scaled method, your ability to most accurately measure what the thickness of the sample is will also propagate in terms of error in what's calculated. And also sample preparation. So, you have to mimic a slab of infinite lateral extent. So again, any way you can prepare a sample to ensure surface roughness, even thickness, minimal spatial heterogeneity will come into play. Anything in an ideal world, we can't manage all of this, but it's clear, it's important to kind of think about this ahead of time and just be aware and cautious whenever you're using this type of technique. Rule number 2 is also know your instrument and the limitations of the instrument itself. So again, as was brought up earlier, these systems are really lossy. So the signal you detect is only a small fraction of the total signal that comes out of the interaction between light and your sample. So, you need to have a spectrometer that's very sensitive and very stable. Otherwise, you just have to be very patient, because any time that it will take, any long integration times, there's anything that can change that you just want to make sure that you have no drift present in your system, your light source is stable over time. Single spheres are easier to calibrate. And again, I was just talking about earlier with the single sphere, but it also requires collimated light. So again, as was said before, this is a particular challenge. There are ways of working around that by using 2 spheres. So you actually would have 2 separate spheres, your sample right in the middle, and one would be your reflectance port. So light would shine in, light going forward, in the one sphere would be reflectance, the other one would be transmittance. And so since it's a single beam making both measurements at the same time, you don't need to have light collimated, so it makes it easier in terms of the instrument setup. However, it's much more challenging to actually calibrate now a dual sphere system. And with Scott Paul's code, he actually goes into great detail as to what those challenges are and how one would approach it. Also, in terms of instrumentation cost, now you have to have 2 of everything. So also then using a variable iris or aperture to control your beam diameter. There's advantages to that, just for the fact that you have to consider in terms of spot size would also affect your side light losses. So you would typically want to have a smaller spot size. Smaller spot size means less light, means weaker signals. So there's always a compromise between how much light you can shine through versus how much more does that complicate your measurement. And the last rule is to have an expectation of what optical properties you hope to measure. So again, having some idea in advance helps a lot, because that will help guide you as to what the optimal configuration of your system is, what you need to worry about in terms of preparing your samples. And so it's always good practice to validate results. So when you're making measurements of a sample, make a measurement of a known reference as well. So there's things like you can use tissue simulating phantoms. You can use short path length cuvettes to measure controlled concentrations of dyes and interlipids or microspheres. Again, you know what the optical properties, the index of your cuvette is. You know what concentration of microspheres, so you could be able to actually predict what kind of scattering spectrum you'd get. Make that measurement with the sphere, does it match up? Just to make sure that your instrument itself can give you reproducible results. Similarly, you can use interlipid, different concentrations of dyes. Do you actually predict and calculate the absorption concentration of whatever dye you used accurately? Because if you can't do that, then how do you know your sample of unknown optical properties will be accurate? So again, we've also used silicone phantoms where you can actually fabricate them in sheets. So you have, again, known thickness, known concentrations of dyes and scattering agents, and you can actually use that as a way of validating your system. Or again, go back to this figure and actually map the optical properties that are calculated onto this parameter space to really see, am I in a range that will actually produce reliable results, or am I collapsing in the parameter space where, a measurement error of 1% would be a 20% error in optical properties. So just know where you stand when you do this. So again, just for the website, I wanted to include a lot of the references that I have used to generate this kind of information in this presentation. So those things that I kind of glossed over kind of quickly, you can kind of look into more detail if you're so inclined. All right. The next thing I wanted to do was kind of give just some examples of how this has been used in the past. So here at BLI, there were 2 different projects that I was involved with where we actually used inverse adding doubling. So the first was characterization of ex vivo tissue properties, and this was geared toward actually looking at optical clearing agents and the performance of optical clearing agents on slabs of tissue. And the second one was looking at generating structured tissue simulating phantoms, where we could actually have layered phantoms with distinct optical properties and then use that to evaluate the accuracies of our just reflectance-based devices. So no longer reflectance and transmittance, but how well can we actually discriminate distinct layers of optical properties with just reflectance-based measurements. So the first project, again, this is a manuscript in preparation, but this was looking at slices of mouse brain using optical properties, or looking at the changes in scattering in these sample slices. And so the kind of scientific questions that were being asked was, to try to have some way of actually quantifying the amount of clearing in these tissue slices and the amount of time that these agents would take in order to clear these tissues. And the actual motivation behind this was a project looking at trying to map the microvasculature in brain tissues in a mouse model. And the interest in using optical clearing agents was that the clearer you can make the tissue, the thicker you can slice it, the easier it would be to map larger thicknesses of the tissue to actually eventually try, the long-standing goal was to map the entire brain in terms of its microvasculature. And so in order to do that in microscopy, I think original papers, they had over thousands of slices, so the goal was, can we just do 10 slices? And that would save a lot more time. But you had to kind of understand exactly what were the mechanisms behind this. And this were some of the images that were produced from doing this. So again, the idea is that without clearing, or only a small amount of clearing, that you could really only visualize the larger vessels within the mouse tissue. But however, after clearing them, and these vessels were tagged by some dye, I forget exactly what, but the idea is that by reducing the scattering, you could increase the resolution and depth. You could visualize these vessels significantly. And so now you can get access to much denser, finer information in terms of the vascularization of these brains. So again, very simply, using inverse adding doubling, we would measure these slices as a function of time, when these clearing agents were applied, and looking at the changes in scattering. Again, this was just a somewhat arbitrary metric of the optical clearing potential of these agents. You can see that relative to its initial tissue state, that you could get up to a factor of 8 reduction in terms of scattering. And we could also do this across all wavelengths, because there were also some other questions of actually understanding how do these clearing agents actually work? What are they changing in the scattering properties of these tissues to make them more clear? So that remains still somewhat of an unknown question, but that was just one kind of example, and it's always great to have cool looking pictures. So that was one example. And then the other example was actually trying to look at developing a quantitative layer-based model for spectroscopic measurements. And again, the motivation here is the fact that there's a problem with making measurements through skin because it's highly structured, and especially the fact that in the most superficial structure, you have highly absorptive chromophores, namely melanin. So there's a large amount of variance there, and whenever you make a measurement, there are certain consequences. So usually quantitative optical methods will report chromophore concentrations relative to the volume of tissue it interrogates. So again, if you have two different distinct wavelengths, and you look at tissue as a simplified layer structure, you actually have different contributions of one layer's chromophores versus another. And so that has distinct potential consequences, which is you have a certain ambiguity in a very general sense of layer thickness versus concentration. So you could have a very high concentration of a chromophore in a thin layer or a low concentration in a thicker layer, and you won't necessarily be able to separate the two. Also, if you're going to be looking across a large spectral range, if your volume of interrogation changes as a function of the wavelengths you're using, it has the potential of actually distorting the spectral content of what you're measuring. So, equations, I apologize, I'll just skip through. But the idea is that what we try to do is develop a method, just simple empirical method to use estimators of penetration depth at distinct wavelengths and model that in terms of saying if I detect a concentration in a certain wavelength regime that only interrogates 500 microns in tissue versus a different concentration of that same chromophore in a volume that interrogates 5 millimeters, I can back out what the layer thickness needs to be in terms of a partial volume model and say, okay, now I know there is a layer thickness that's this thick and the concentration specific to that layer is this amount, as opposed to average amounts of things based on the volume you interrogate. We've done simulations of this, and we're able to kind of go through and, in fact, from simulations get reasonable estimates. So if you had a simple, and again this was just multi-layered Monte Carlo simulations where we just varied the top layer thickness, fixed the melanin concentration to 1% within that top layer, oxy and deoxy to a fixed percent in a bottom layer, and just said, if I simulate my measurement type, what are the differences in terms of the absorption spectra will I see? What are the differences in the penetration depths I can estimate? And can I actually use this empirical model to back out what the concentration is? And so in simulation, we were able to get within 5% of the actual melanin concentration, whereas if we only used the spectral content in the visible or the near infrared, it was grossly underestimated and also sometimes very depth specific, layer specific. But that was simulation. So what we wanted to try to do is experimentally validate that. So we used silicon phantoms where we could actually have discrete optical properties and discrete layer thicknesses, stack them, and say, can we actually do the same thing in a physical measurement? So of course, we fabricated these phantoms, and again, ideally to try to mimic the actual structure of tissue itself. So again, just a high frequency ultrasound image of skin versus this stacked phantom. And in order to actually validate what are the optical properties of these thin slabs, of course, we want to use inverse adding doubling, can quantify them, stack them, make measurements, and similar to the simulations, so now we have two layers, two distinct absorbers, and try to back out, and here again from experimental measurements, we're within tens of percents of the actual values, where if we just use a homogeneous model, we're going to be grossly underestimating the values. So that was just another case to actually go through in terms of validating measurement accuracy in terms of structured tissues, that this can be employed. So, any questions about that?
Can you go back to the slide where you have the different curve on different region, near infrared? Yeah, go back. 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 Yeah, the previous slide. Yeah, this one. So here you on the graph you have a spectra and you have two regions. One is in the visible. And one is the near infrared.
Yes.
And on the table you have the last column mean visible, near infrared only.
Yeah.
And you have two numbers. What is the
So
meaning of that?
from the simulation, what I did is, in addition to try to see how accurate I can use the kind of differential penetration depth between visible and near-infrared spectra, I also asked the question to say, well, what if I only had a system that only had visible spectra, and I just fit for the chromophores, what kind of values would I get? And so that's what I did, is I just segmented, right down at 650, and tried to fit for oxy, deoxy, and melanin from 650 onto 1,000, and then did the same thing from the visible, and just used that in a kind of homogeneous model sense. So if I just assume that, all right, I'm measuring chromophores, they're evenly distributed, what would it say the melanin concentration is if I don't know the depth? And so what we're looking to try to see is, all right, how does this depth, this variability in thickness really affect our estimation of the concentration? Is there going to be a strong dependence towards the accuracy based on this layer thickness, or what are the consequences? So
the number here is the actual precision or the actual number?
So this is the actual concentration. So again, if the actual concentration of melanin in that top layer is 1, meaning 100%, if I only use the visible data, it would estimate a 21%. So
the lesson here is you cannot use visible or near infrared. You need to use a wideband to have an accurate prediction.
that's the argument I want to make. I mean, there's also a lot of things of asking the question of whether it's relevant or not. So I mean, there's a lot of different methods where knowing what the actual concentration of melanin is not necessarily the most important thing. The most important thing is knowing how to minimize its effect on everything else. So there, you don't necessarily need to calculate it and know how thick it is or how deep the melanin is. You just want to manage that and move on. So, this was another case. I mean, what my research was trying to go towards was actually looking at melanomas, where again, you have thickening of the epidermis and a change in concentration and potentially a shift in the spectral signature of melanoma. But without decoupling how thick it is, you wouldn't really know what the concentration within that tissue would be. And then you wouldn't have the opportunity to really even look at, is the spectral shift a consequence of the thickening of the tissue, or is it specific to the melanin itself within? So that's the kind of motivation behind doing this.
Thank you.
Yeah.
So for the limitations that you mentioned and the rule of thumbs 1, 2, 3, you mentioned there were some of the geometrical issues and various aspects that you need to take care of while designing the system so you can reduce the errors. The question is, I know it's kind of a broad question, but do you have any idea which ones of those are more detrimental to the accuracy of your measurement? And are there any examples that you can quote to say what can you expect? For example, if you try to measure intralipid scattering or a known absorber, what is the error range you can expect, and what some of these errors may introduce?
Yeah, so in terms of, trying to come up with independent validations of the accuracy of the system, there's always some variability. There's a lot of literature out on intralipid, and from source to source, what are the variations from day to day, temperature sensitivity. So there's usually a general trend that's been characterized, but yeah, there's always going to be inherent variance to that. If you really want to be accurate, microspheres, you know what the distribution is. You can go to me theory and actually predict what the scattering should be, measure that. That's a little bit more reliable, but it tends to be more expensive and, somewhat more tricky just to maintain the distribution of the microspheres. So there's some other considerations there. So there's, a bunch of different approaches, but for the most part, for the afternoon labs, we're going to just try to go through with simulated data to say, what if you're slightly off on this value or that value? What happens? What happens when noise is introduced to the system, and how does it affect everything downstream? Just to kind of give a more general sense, because there's a lot of different factors involved based on the different components you use, the actual alignment of the system and how accurate you can do that, how stable things will be. So, there's a lot of different things, but that's where it's always important to have a sanity check whenever you're making a measurement, just to really get that sense.
As kind of a follow-up question to his, what would be the drawback of using like a solid reference, like the silicone filled with an absorber?
So the actual physical measurement aspect of the lab today, you'll be making measurements of silicone sheets with titanium dioxide and dyes in them. And the one limitation is that when you're making silicone phantoms, it's not a direct approach. I mean, the actual recipe, there's a lot of different factors going into the fabrication. So you will have target optical properties when you fabricate the silicone phantoms. What you actually get when the phantom cures is not necessarily exactly what you put in. So the accuracy of dyes and scattering, because again, you're talking about usually titanium dioxide, which can aggregate. So you never really know exactly what the scattering properties, what the average particle size will be when you fabricate these. So there's a certain limitation to that. So, there's always going to be caveats, and that's where for this study, I went through and fabricated them, had some idea of what the optical properties should be, and then used the inverse adding doubling to verify what the actual optical properties were. So in order to kind of lend some confidence to those results, I actually used microspheres to as a means to actually determine the accuracy. I was able to determine the optical properties of the sphere and the setup that I had. So, but once you do that, the nice thing is that the silicone tends to be stable over time, that if you can measure it once, you can always then use it again as a reference in a sanity check over time.
Are there any companies that sell like standard references? I know Intraliquid may be something like that, but I would assume there could be something better that you could forward us to.
Yeah, I mean, in terms of thin samples, there really aren't many. I mean, outside of, there are some individual research groups that have published methods on making thin samples, here being one of them. In terms of optical phantoms, the only company that I could think of is INO in Canada. But outside of them, I don't know of any actual commercial entity that actually would sell optical phantoms or references for turbid samples. So that's always, one of the weak points right now. But again, honestly, there's not that much of a market for these things anyways, so it's difficult to be a company that would just sell phantoms. All right.
Hey, Ralph, just a practical question in making multi-layer phantoms. When you make those, do you actually make the layers separately and then put them on top of each other? Do you actually pour the silicon that's still uncured on top of a cured silicon? And if you don't do that, how do you take into account the air gaps between the two layers?
Right. So the method I actually used, I made individual sheets, and I could actually physically stack them. So the nice thing there is I could have a base phantom where I know the optical properties and make measurements of thin sheets that I knew what the thickness are and interchange them. The one nice thing is with the silicone, there's a little bit of an electrostatic surface, so you could actually place the sheet on there and actually push out air bubbles and actually have tight optical contact without having to have any intermediary substance in between. I mean, that's a little loose and free, but, I mean, the nice thing is that if you're making a phantom and then you pour something on top, it's very difficult to independently verify what the optical properties are or know what the actual thickness is. And so with these phantoms, we're trying to do things that are like 150 microns thick. That's pretty hard to guess while you're pouring. But all right, well, I think I'm just going to end it right here. And no, not really. So, I mean, the last thing that I wanted to just talk about is try to put this in context of other methods in inverse solver tools. So yeah, I mean, again, just to kind of draw everything together in terms of when would inverse adding doubling be an appropriate tool, is again, it has certain strengths. Each step of inverse adding doubling, or even just the adding doubling method itself, the forward model, has a direct physical interpretation. So again, it's always being described things in terms of radiance, which you can, measure in terms of reflectance and transmittance. It's very insensitive to optical properties over a wide range. It employs steady state methods, so somewhat simplifies the costs of instrumentations, but the cost of doing that is the fact that if it's too simple of an instrument, it'll never be accurate enough for what you need. So there's always some trade-offs there. But the drawbacks for inverse adding doubling is if you're interested in calculating internal fluences, this is not the tool for it. So, even though it's a 1D simplification, there's the issue of uniform illumination. So again, making physical measurements, keeping everything evenly distributed and collimated, it's a subtle art. And again, it has to be layered and it has to be evenly distributed within that layer to actually understand what the optical properties are. So, and then in the next few days, there's going to be other reflectance-based methods. So again, inverse solving, inverse adding doubling, you had a simplified model that described reflectance and transmittance in terms of absorption and scattering. So you have two measurements, two unknowns. There are other ways where you can just make reflectance measurements and then modulate either the detection or source geometry or properties and use that to tease out so you actually get multiple pieces of information from just a reflectance measurement. And I wanted to also point out that these approaches can also be complementary in certain cases. So if one has its certain strengths and weaknesses, another one has a different strength, there may be an opportunity to have them work together. But of course, that adds complexity to the measurement, compounds the limitation and constraints on what type of tissue you measure, but can help overcome some of the ill-posedness problem that seems to creep in no matter where we go. So that's it for today, I guess.
So I have a very specific question. I don't know if it's really related or not. So I'm developing optical system for clinical trial. And what we are facing is right now having different systems, different optical probe, and we need to validate them so that we measure the same result coming out of different system, different probe. And we have a hard time to do that right now because we don't have the standard sample from INO, yes.
Right.
And we do not know what is the best way to do that. Meaning we can account for different system and probe. And when so I bet that one thing that we would think of is have a reference sample, very solid like INO sample or silicon, measure them, simulate them, and go back and check our instrument. I don't know if it's a good way or is there any suggestion
Yeah, no, I mean,
better way to do that?
when it comes to doing multiple instruments and cross-validating, I mean, that's always a very tricky and challenging problem. So, yeah, I mean, I think, it's a very reasonable approach to have a single reference phantom, make measurements from the different systems, look at where the differences are. But, that's also a very complicated problem. There's a lot of different other factors, and so, it's at least a measure of something. I don't know if it's going to solve the problem, but I mean, I think, oftentimes when you have something and you have multiple measurements from a single device or multiple measurements from different devices, that there's a lot of ways that things can kind of go askew. And, I mean, at least having the sample be a consistent reference sample at least is one starting point that you can move forward from. So, I mean, yeah, it's typically for the instruments that we have here, we actually make a reference calibration every single time we use it because we don't know what might change in the state of the instrument itself. And so that's always been the kind of cross-reference to say, can we account for any instrument function that has changed from day 1 to day 2? But, yeah.
So my question is, you're talking about measurement of the system before measurement. So it
Yeah.
is in the lab or in clinic or both?
This is in the clinic, usually.
In the clinic?
Yeah, so I mean, typically we will make these silicone phantoms and bring it with the instrument. And so at that point in time, who knows exactly what might be going on. We have broadband light sources. They will change over time, but change rather slowly. We actually have ways of controlling the flux, and so we can actually have a feedback. But, at that state, we always want to make a measure because also we have multiple people who are using it, so something might have changed, somebody might have tweaked something. So, that's usually the safest and most cautious approach. But yeah, I also know that when it comes to looking at multiple instruments, making measurements, that, it's a very challenging aspect to make sure that every single one can produce the same quantitative result you're looking for. But yeah, I don't have any specific suggestions for that.
Oh, the question is how many samples do you measure before the calibration sample? How many? You just measure one?
Yeah. So we've taken a long time to really make sure that we actually have validated that reference sample and that the optical properties are quite accurate for that, and then go from there.
Thank you very much.